Our next speaker today is Dr. Maaike Vercauteren. Maaike got her PhD in vet medicine and her master's degree in biology, both from the Ghent University in Belgium. Currently, she is a postdoc researcher in the Blue Growth Research Lab, Laboratory for Environmental Toxicology in Belgium, where she coordinates all microplastic research in the group, including study on the thinking behavior of plastics, environmental effects and monitoring, and the human health effects. Today, she is going to talk about method standardization and a technical development for FTIR and ATR-FTIR analysis in Belgian research. Please join me in welcoming Dr. Maaike Vercauteren.
Hello, everyone. Thank you for inviting me here. I want to talk about method standardization indeed. And I want to start my presentation with this slide and with this quote from Jacques-Yves Cousteau. Water and air, the two essential fluids on which all life depends, have become global garbage cans. So this picture and this quote capture the essence of the global plastic problem. And it was confirmed quite recently again when they found a new species. So they never found this species before, and they found it 7 kilometers below the sea surface, and it got a name that ends with plasticus because they found PET particles in this organism. So they never even saw the organism before, and still it had plastic in there. So plastic pollution is a worldwide problem. But how does it get there? How does it get in this amphipod that is swimming in the deep sea, and how does it get in the environment? Let's have a look at the life cycle of the plastic. So we start with the production of raw materials, so the nurdles or the plastic pellets, and they are converted into plastic products, so in a drinking bottle or something like that. Then we have the user phase, when the plastic bottle is in the supermarket and you buy it and you use it, and then you have the waste. So you don't need the bottle anymore and you throw it away. So where does this problem of plastic in the environment comes from? We have two options. It could be the fact that plastic is just a very large production, is plastic production. So we have a worldwide production of almost 370 million tons in the world. So that's a lot, and it's expected to be increasing in the next couple of years. So plastic production could be a problem. But it also could be that we are the problem. We lose the plastic when we transport it. We sometimes illegally dump the plastics. We even make products that are designed to release microplastics. I'm thinking about personal care products like scrubs and so on. There are plastic products that wear off materials. And we also are not managing our plastic waste properly. So we lose plastics, we spill them, and they get into the environment. So there are a lot of different products. So plastic production itself and the large plastic production itself is not the only problem. Another problem is the fact that we don't take care of these products and they end up in the marine and aquatic environments. Another problem is that they are very resistant, and this resistance causes them to last for a long time in these environments. So let's say a plastic bottle can last up until 450 years until it's gone. And even when it's gone, it's probably not really gone. It's probably degraded into small plastics. Because microplastics, so big parts of plastic that come into the environment, will degrade into mesoplastics, microplastics, and nanoplastics. So they always get smaller and smaller, and we don't even know if they will disappear at all. But they will not be visible anymore. But when they are getting smaller and smaller, the group of organisms that comes into contact with them and can ingest them will also grow bigger and bigger. So the effects might also be related to the size of these plastics. So what are the remaining challenges in this research field? Because plastic pollution is not really a very old research field. It's a very new one, and there are a lot of gaps in the knowledge. We still don't know the exact concentration in various ecosystems. We don't have a lot of information on the smallest microplastics, and the nanoplastics is even less knowledge about. We don't really know ecosystem effects. We're still looking out for trophic transfer, biochem accumulation. We still have a lot of questions on the flux of plastics towards the marine environment. We know that some of the plastics will sink to the bottom, but we don't know which actions can reverse this movement, or if this is something that is dynamic or more static, or what are the influences of this processes. The effects of humans are something that is even more quite a bigger question mark. Effects for animals, risk assessments on nano and microplastics, and the list goes on and on. So there's a lot of things that we still have to figure out. And all these research questions all rely on good methods for sampling and analysis. That is a very important one, because the methods you use will have an effect on how good your analysis is and how good we can fill these gaps of knowledge. So let's have a short overview of the history of Belgian research in plastics. So in Belgium, the research started around 2002. In our research group, the Gentox lab, so the environmental toxicology lab or unit, started in 2005. So what we did in the past, we started with studies on microplastics on beach and on the seafloor. So we started at the Belgian part of the North Sea. We collected samples and we analyzed them, and we found plastics. We found quite some plastics in beach, in the seafloor, and sea surface. Everything that we looked for contained plastic. And then we moved more land inwards. We moved to the Schelde, and we looked at the riverine concentrations of microplastics. Then we moved to sewage treatment plants, where we figured out if they are cleared from the inlet of the, or the influence of the wastewater treatment plants. And then we moved to the marine invertebrates, where we connected with the human health effects and what we can take in as humans. So in everything that we studied, we found microplastics. So this again indicates the global distribution of these plastics. And for now, we are working on plastic flux from inland to sea. We are looking into ecosystem effects for the smaller microplastics, human health effects, but also monitoring studies where we want to create a baseline for future evaluation measurements. And we want to look at the method development, of course, also. So in this short time between 2005 and now, we went from sea to source, so more inland research, and then we moved on to the effects. And we tried to do everything still. But as we moved more inland and more to the effects, there was also continuous development and refinement of the different techniques that were used, different equipments that were used, and the analysis of the data. So how we do the research now is quite different from how we did it in the beginning. So I wanted to go over the methods we use for collection of samples. So we use various different matrices, and each matrix has different complexity. And with complex, I mean particulate matter that is in there, or other organic compounds that are hampering evaluation or hampering analysis. So there are different degrees of complexity in those matrices, but we can divide them into water samples, sediment samples, and biota. So water samples, we have protocols for drinking water, for surface water, for wastewater treatment plants, for road runoff. For sediments, we have sediment of rivers, but also remove biosoils and sand fractions of wastewater treatment plants. And for biota, we have protocols for different kind of species. And during all those samplings, we try to focus on a few things. And these are also, those focuses are also changing over time, of course, because every sampling we do, we learn things that can be better in the next phase, of course. But generally, we try to integrate samples as much as possible to decrease the variability. We take a lot of replicates to incorporate temporal variations, so replicates in time. We also include different locations to incorporate spatial variation, because that is also very important. And as much as possible, we use automated systems, because we saw that when we use automated systems, so that means that there's a machine that takes the samples, and we don't have to handle any samples, and this decreases the contamination of the samples a lot. So this will not be always possible, of course. So it's not one size fits all. We cannot find one protocol that is good for every one of these matrices and every situation. So we have to see, based on the samples that we get, we have to see which protocol is the best. So I will show you a few of our slides from how we do the sampling. So water samples, from surface waters, we use bulk sampling. So we scoop some water and we transfer it to a glass bottle, and then we analyze it in the lab. Sediment samples, we mostly use Van Veen grabs and transfer them to glass jars. And for biota, we also use nets and filter the water there and keep them in inox buckets. Sorry. For wastewater treatment plants, we use an automated sampler. So this sampler uses, so it takes samples during 24 hours, and every 30 minutes it will take 200 milliliters of water from influent or effluent of wastewater treatment, and it pulls all those samples together. So this this makes sure that we have a large time frame covered, and we can decrease the variability a lot, because we have a lot of individual and small samples, and we can all sum them into one big sample. So when the samples are collected, they move to the laboratory processing, and we start always with digestion, depending on the matrix, of course, but in most environmental samples, it's necessary to do a digestion. And here also, it's not one size fits all, because we have water samples, sediment samples, and biota, and every sample has an own protocol. What we did was testing the protocol for its efficiency for digestion, because it's very important that samples are digested well. But we also looked at the effect of the digestive products on the plastic itself, because we don't want to use any product that can degrade the plastics or can have an effect on the plastic, because then we would do wrong things with our samples. So we just put some virgin plastic material, and we added KOH, which we use for water samples, and hydrogen peroxide, which we mainly use for sediment samples. And we put it together and we sampled it in regular time frame. So 1 day, 2 days, and 3 days. And then we did an analysis using the ATR-FTIR. And we checked if the spectra were okay. And we saw indeed that even when they are in high concentrations of hydrogen peroxide for 3 days, then the spectra of all those main plastic types remain the same. So The digestion protocol that we have used has been checked, so it's efficiently in digesting the samples, and it's also safe to use for our plastics. So next to digestion, we do density separation. So this is based on a dense sodium iodide solution, and the goal there is to make all the plastic material float, and all sediment particles and others to sink to the bottom. So we collect the supernatants of this density separation, and we move on with that. And then we have filtration. So during the whole process, we filter using cellulose nitrate filters. And those filters are collected and then digested again. And then we put everything on a PTFE filter that we use for analysis on the FTIR. So that were the methods for sampling of the samples, so collecting samples. And now the methods for analysis of the microplastics. So as you probably all know, there are a multitude of analytical methods available, and all methods have their own characteristics. So some of them will measure mass, some of them will measure particle characteristics such as size and shape and so on. Other will count the plastics and so on. So they all have their benefits, drawbacks. Yeah, and we have to choose some techniques. One big difference that is dependent on the technique you use is the reporting unit. So you can report the plastic pollution in mass, so grams of microplastic per volume of water, or you can report them in numbers. So when we move down to the nanoplastics and look at the evolution in analytical techniques now, we see that there has been a shift towards mass-based analytical methods, and we kind of move away from the number of particles. And this can have a large effect, of course, because for mass, the bigger particles, the big plastic, the macroplastic, will have a lot of input in the mass. So if you have one large bucket, it will have a lot of impact on the total mass of the sample. And the smaller plastics, they will not. But in the number unit, we have the opposite effect. So the smaller particles will have will have a larger effect on the number. So if you have 100 nanoplastics, you probably will not have 100 cans of macroplastic. So in terms of number, you will probably have more weight on the smaller particles. But in terms of effects, that's a big question, because when you report mass, you will not put the emphasis on the smaller particles. When you report number, you will put the emphasis more on the smaller particles. And the effects will probably have more to do with the size of the particle and not with the mass of the particle. So the unit which you use for analysis will have an effect on what you can say about risk for the environment. So a common approach until a few years ago was a visual inspection and analysis. So you take your sample, you digest it, you filter it if necessary, and then you visually inspect it under a microscope, and you can see, you select the particles that look like plastic, and then you inspect them further. But the problem with that is that you might cherry pick your results. So you choose which particle will be analyzed further. And then you have to be critical and ask yourself, are you really sure that you have found every particle that is in there, or can you miss some particles just because they don't look like plastics for you? So we use another method using FTIR spectroscopy, and there we chose to identify all particles on the filter surface. So we filter our whole sample on a PTFE filter, and this filter will be scanned entirely by the FTIR. We analyze in reflectance mode, and we use the particle wizard for analysis. So I'm going to take you through our workflow. So we start with a filter, and we take a mosaic picture of the PTFE filter. So a stitching of all little pictures, and we cover the whole PTFE filter surface, or at least where the filters went through. Then the second phase is to select the particles based on light and dark thresholds. So we select which particle had to be analyzed and which not, but just based on the darkness on the picture. Then we do spectroscopic analysis of all selected particles. We do a background correction for the PTFE filter, because PTFE is also plastic and it gives some background. So we do, on every filter, we do a background correction, and then we compare the results. So the measurements subtracted by background, and then we compare these results with the library. And we have both an in-house library that we have put together ourselves using these PTFE filters, and we also use commercial libraries. I would use them both, they complement each other. So we are quite happy with our workflow, but still we need to remain very critical. Are we sure that we find all plastic particles, even if we scan the whole filter area? So what could be a problem in doing this analysis? And if you look at the size distribution that you see here from one of the samplings we did, you can see that when you go to the smaller sizes, so here between 0 and 30, you have less particles than the category of 30 to 45. So are there really less particles in these categories, or do we fight the boundaries of the equipment and the protocol? So the smaller we get, the smaller particles, the more unsure we are on the measurement. And there could be a lot of difficulties for these smaller particles. So smaller particles could be already a longer time in the environment, so they might degrade it more, and this might cause spectral deterioration, so that the spectra that we get are not matched to the known spectra. They also can be overshadowed by background because they are so small. And smaller particles are easily lost during the process. And if we look at it, we go a long way from sampling to analysis. And it could be that we lose plastics. We can add plastics by contamination. We can overlook plastics. We can falsely identify particles, and so on and so forth. So there's a large need for method standardization, but also for quality control and recovery experiments to analyze how good we are at measuring those samples. And it's not only our lab, it's a general and global problem that we need standardized methods to analyze all these different segments of plastic pollution. And this is a work that is in progress in many different labs. So I mentioned also quality control of the data, and I want to present how we deal with the quality control of our data. So what we do is we calculate for each of the matrices. So let's say drinking water, then we calculate an LOD and LOQ, so limit of detection and limit of quantification for each of the matrices we use, and for each polymer type. So each polymer type and each matrix will get one LOD and LOQ value. And when we find a value in our sample that is higher than LOQ, So LOD and LOQ are based on blank samples that are collected in roughly the same manner as the real samples. So then we calculate the LOD, LOQ values on the blank samples, and then we compare these values to the real samples, the real environmental samples. And if they are higher, if the concentration of plastics is higher than the LOQ value, then we estimate that the quantification will be reliable. So we find enough particles so that we are sure that they are not due to contamination, for instance. If we find a concentration that is between LOQ and LOD values, then we are more conservative and we say that there are plastic particles present in the sample, but we cannot reliably quantify them because it could easily be some contamination. And when they are lower than LOD, we assume that no plastics are present. So that is how we deal with the quality and the quality control of our samples. But even in this, there's a lot of different methods that have been used or that are being used in different labs. So even quality control should be something that is standardized over the labs. Then I want to go over the Belgian research. So what are we doing in Belgium on plastic pollution, and how are we studying it? So you can divide the project that are currently running in 4 categories. We have monitoring of plastics, where we have, for instance, a Pluxin project that studies the flux of plastics from inland to sea. We have effects on ecosystems. We have method development, where we want to, like the EuroCharm project is based on or is working on method standardization. And we also have human health effects that we are working on. And there are a lot more. I just gave some examples in each category, but there are a lot more, of course. So to end my presentation, I want to go over some future perspectives, or what we would want for future research, or for future techniques for microplastic research. And the problem is a little bit, you kind of want it all. We want to measure smaller and smaller particles. We want more complex matrices. We want to measure all different types of microplastics. But next to that, we also like to characterize shape, color, size, polymer type, mass, and so on and so forth. We want no contamination, no false positive or false negative measurements. And we want it fast and cheap, of course, also. So we have a lot of future perspectives where we can work on, and I think there's a lot of challenges in the future for us. But as this picture say, the next big thing will be a lot of small things. So we are very excited for all the challenges we have to face, and finding solutions to analyze microplastics more reliably in the future. Thank you for your attention, and hope you have enjoyed my presentation.